Swayam Prabha. Digital India. Educated India.
So focusing on transistor level things, right? We'll just very quickly derive what is the maximum gain that is available in terms of Y parameters, and then we will look at a transistor model and learn from that, right? So let's say that I am now, instead of S, because Y is a little more intuitive from a circuit's perspective, right? When you're going from low frequency to high frequency. Let's just model this that I have a source that is Is with a resistance that is Ys, right? And then this is the model for my device, right? So the first question that I can have is, what is the power that is available from this source, right? Let's say that I'm terminating things in a YL, okay? If eventually we'll make the YL the conjugate of what we see over here, right? But let's begin with this. So if we see what the Y in is, right? For maximal power transfer, we have done conjugate matching, right? We do conjugate match. So we know that Yin is Ys conjugate, right? Or basically real part of Yin is the same as the real part of the Ys, right? So if I then basically think about the power that is available from the source, I can show that it is basically Ys squared divided by 4 real part of Ys, right? So I can basically say that this is the situation when half the power that is available is dissipated in the source impedance. Half of it is dissipated into the Yin, right? But we know this condition is satisfied, so we can basically say that the P available from the source, or the P in that is going in, is Is squared divided by 4 real part of Is. And then what I can do is, I have this Y parameter network, right? And I have Is, Ys, right? And I'd like to instead model it as a I equivalent here, and then with some Y equivalent, right? And this is basically driving my load, right? So I'm trying to find the model of this when it is driving my Y load, right? And try to model this part over here, right? With this, right? And in order to find that, you can just basically short circuit the output in order to find out what IQ is. And just from Y parameters, you can show very quickly that YQ is just minus Y21 times Is divided by Y11 plus Ys, okay? And you can basically show that you get some YEQ, which is Y out, right? Which is basically Y22. It's here. So it's Y22 minus Y12, Y21 divided by Y11 plus Ys. Okay. So we can build the model for this network, and then the maximum power that will be transferred into the load will just simply be IQ squared divided by 4 real part of YEQ, right? Which is the same as IEQ squared divided by the 4 real part of y out, right. So, you effectively then have a situation, right, where the maximum in the situation with conjugate matching, right, you are basically looking at a power gain of IEQ squared divided by 4 real part of y out divided by the power that was available from the source, which is IS squared divided by 4 real part of YS, right. So, this basically then becomes Y21 squared divided by Y11 plus YS. Sorry, this should be erased here, times real part of ys divided by real part of y out, right. So, we effectively now have a situation, right, where you for conjugate matching we know that ys is yn conjugate, right. So, we can then further express this as y21 divided by y11 plus ys, sorry, y11 plus y in star squared real part of y in star, which is just the real part of y in divided by real part of y out, right. So, you have this situation, right, and I mean both of these are the same whether you do real part of y out or y out conjugate. So, what you effectively see over here is, remember that y out is a function of s, right, and y in is a function of yl, right. But we are also imposing the condition that ys is y in conjugate and yl is y out conjugate, right. So, this implies that y out is a function of y in, right, and y in is a function of y out, right, for conjugate match, right. Both of them interact with each other, and you have this equation for the maximum power gain, right. So, then you can basically show effectively that in this situation the maximum power gain that you get is y21 divided by y12, right, times k minus square root of k squared minus 1, where this k is the Rowlett stability factor, right. And this basically says that this is the maximum gain that you can get from the transistor once you conjugate match, right. So, of course, there is a situation here that what if k is less than 1, right. This then says that you do not have unconditional stability, right. So, when you do not have unconditional stability, your transistor is potentially unstable, there is really nothing called maximum gain, right, because then if my transistor is unstable, it can oscillate. So, an oscillation is basically infinite gain, right. I am not providing any input and I am getting input power and I am getting the output at that frequency. So, it is effectively infinite gain. So, there is no meaning to the word what is the maximum gain if I am not unconditionally stable, right. So, what we can then say is that we usually define something that you might have seen, which is what we call maths stable gain, right, which we say is y21 divided by y12, right? But this is not meaningful. It is just a guess, okay? It is just a guess. It basically lets us compare two transistors, right, for example, but this is just a guess for what is the gain that can be achieved. Because right now my transistor is not unconditionally stable. So what do I have to do? I have to search through all possible gamma S and gamma L, right? And there might be some gamma S, gamma L combination where I satisfy the conditions that gamma in is less than 1, gamma out is less than 1, right? So search all possible gamma S, gamma L, right? There might be a condition where this is satisfied. So now my network is stable, right? And then you look for evaluate gain, right? And you do this loop until you find what is the maximum gain that is possible. That is what you would have to do in this scenario, right? So the G math stable gain though is just a guess, right? It says what is the gain that you would get if K was equal to 1, right? And so basically it's G maths when K equal to 1, right? If, I shouldn't say when, if K is equal to 1, right? But you don't, you don't know in this situation, right? If this is a meaningful metric at all. Does that make sense? So G maths is very clear if K is greater than 1. Because then you can say, okay, if I put a conjugate match at the input and conjugate match at the output, this is the maximum gain I'm going to get, that I can get, right? Does that make sense? And you can clearly see over here that as K tends to infinity, that G maths tends to 0, right? Because K minus K squared minus 1 goes to 0. So having a lot of K is basically also saying that the maximum gain is going to be reduced, right? So this is again just an intuition that if there was a way by which you can trade off some of the K in order to get more gain, that is possible if you build a network around it, the transistor, right? So people in recent research have shown such networks that basically if you consider the transistor network, right, and in there you basically put a embedding network around the transistor, right, and this network is basically you can clearly see that this network has, the embedding network has a port 1, I can call it a port 1 prime, has a port 2 prime and a port 2, right? So it effectively has a 4-port network, but you can put an embedding network around your transistor that effectively gets you gain higher than what G maths is, right? Because G maths just is the native transistor's Y parameters, because this K is computed from the Y parameters. But when you put this de-embedding network around, you are changing the parameters, so you can basically get a gain that is higher than G maths with this. Does that make sense? So G maths doesn't mean that this is the highest gain that you can get from the device. It only means this is the highest gain you can get from the device if the network that you're putting in around your device is a matching network on the left and a matching network on the right, right? If your network looks like this, where you have a matching network on the left and a matching network on the right, right? Then you can basically say that you'll get G maths if you make this conjugate match to the right optimum impedance, etc., right? But if you build your de-embedding network like this, like a 4-port network which has feedback around your transistor, you can possibly get a gain higher than G maths, right? That's possible. And GMSG is again It is just a best guess for the gain that you can get. If you really wanted to find out what is the maximum gain that you can get, what you would go is search through all the source and load impedances, find out some that satisfied this condition, evaluate the gain for that particular source load, and then keep searching through all possible source load till you found the best possible gain. Right? But when you did that, in this case, what will happen is that your network will be will be conditionally stable. So it will only be stable around that particular impedance that you choose, right? So you have the same problem that we discussed earlier, which is that you have stability circles that you have to work around and make sure that your device is stable. So all the simulators will give you this parameter and this parameter, right? So they tell you how well you can do. And what is actually useful is that when you are designing, you can very quickly get an estimate of how much gain you can get by looking at GMATs. And GMSG, you can take a look to just see if, that's sort of like the maximum that you can get, provided you impose like k equal to 1 somehow, right? There is another gain that people talk a lot about, which is called Mason's gain or Mason's unilateral gain, right? And what this gain basically talks about is that you have your transistor, right? You have your transistor, and then you put some network around, right, over here. So this is transistor, and this is some other network that I'm adding, right, which is lossless. Right? And what basically I'm trying to get from this network is that I'm trying to get my Y12 to go to 0, right, for this entire network. And what Mason's gain, unilateral gain, the reason why it is interesting is a couple of things. One, it is invariant. So basically it doesn't matter how you do this, right? But once you do this, the maximum gain that you can get is given by this parameter u, which is y21 minus y12 squared divided by 4 times, I guess, real part of y11, real part of y22 minus real part of y21, real part of y12, right? So this gain is invariant to how you accomplished the, this should be overall, right? And this is the original network that you started with. So I'll just call this the transistors network, right? The original transistor network that you started with, right? And this is the overall after you have added this network to get y12 equal to 0. So what this is saying is that if you figured out some way to remove y12 in your network, right, you can get this much gain, and it doesn't matter how you get it. And what is really interesting is that when u where u goes to 1 or 0 dB, right, is the at some omega, right, at some frequency f equal to f max, right, that is also the frequency at which g max goes to 1. Right? So what basically people found, and you can show that U has a 20 dB a decade slope, right? So what people used to find easy to do was to measure U at a somewhat higher, measure the transistor at a somewhat higher frequency, lower frequency, measure U, right? Extrapolate from U what the F max is, right? So basically you would measure U at some frequencies, apply the minus 20 dB a decade slope, and you would get F max, right? and you could then use that fmats to know where your gmats went to 0 dB, right? So it's like a two-step process where you are able to, so gmats doesn't have the slope property that U has, right? So it is sort of useful to be able to determine what the fmats frequency is using this Mason's invariant gain parameter, right? But Mason's invariant gain is also not the maximum gain in your system, right? This is gain, so people will call this the maximum unilateral gain, or this is basically the gain, best gain that you can get if y12 goes to 0, right? So all of these gains in the system are all under very specific conditions. Gmats is you are not doing anything else to your transistor, you just have a network before and after, right? GMSG is you arbitrarily put k equal to 1, right? There is no real deeper meaning than that. It's an estimate of the gain that you can get. And Mason's unilateral gain is the gain if you make the transistor unilateral. Why is this useful? Another reason is that making the device unilateral or moving, like for once you make this the network y12, right, overall, you make it 0, then if you are looking to match the source and load impedance, they don't depend on each other, right? So then it's very easy for you to design because you can just figure out what is the input impedance that you see here, and then you can find out the matching network to go from ys to ys mats, right? And similarly, here you can go from ZL to ZL mats. You don't need to worry, you don't need to design both of them together and solve those equations, right? So this is again very useful if you're designing unilateral amplifiers. Does that make sense? So in practice though, when we are actually designing on the chip and with all the tools, simulation tools that we have, we don't need to constrain ourselves to making the device unilateral, right? We can live with some y12 and still be able to get better gain in the system, as long as we get unconditional stability. Does it make sense? So what is though interesting is that this GMATs though gives us a clear metric for designing, in the sense that now I can try to take my transistor and try to optimize the GMATs that I get out of it, right? Because then if I optimize the GMATs that I get out of the transistor, I know that I can design a network which will get me that GMATs, right? I can make that my design principle.
You can make the transistor unilateral.
Yeah.
Gmax may go to infinity.
Yeah, no, so you're not making the transistor unilateral, right? You're making the network unilateral, right? And the thing is that when you, this K also depends upon Y, so if you consider the network overall, this K depends upon Y12 as well. So just because you're making Y12 0, you're also basically, this K is a function of Y12. So it doesn't, or the overall network gain doesn't go to infinity. Does that make sense? So yeah, I mean, this is a question that, you know, that comes up, which is that if I make the device unilateral, y12 goes to 0, and then this, blows up. But that is conflating two things, right? This is the network, and in the network you are making y12 0, right? And once you make y12 0 in the network, the k minus k squared minus 1 also has a y12 parameter in it, right? So that though that y12 sort of cancels, so you do have a finite gain that you can get out of the system, which is the unilateral gain that you can have. Does that make sense? Demonstrate this in the technology that you're working with, right? I ran some simulations of on just an arbitrary device, right? And this over here is what you see is U, right? And this is GMATs and MSG, right? GMSG. as I mentioned, at all these frequencies up here, basically what this is implying is that K factor is less than 1 at all these frequencies. And you can see that this transistor, because I'm just taking the native transistor and simulating, I'm not putting any parasitates resistances in and around it, right? You can see that this transistor is not unconditionally stable until very high frequency. But you can see also what I said about U and G mats crossing 0 dB. So this would be the F mats of the technology, which is somewhere around 260 gigahertz. Right? So this is the frequency at which your power gain goes to unity, or you cannot get gain out of this device. And what is interesting is that if you do all that de-embedding network, etc., right, even with that, your F mats doesn't change. Your F mats still remains the same. You can do all that de-embedding network and get gain that is higher than this, right? But your F mats will still stay the same. So the F mats is actually a really good metric of performance of the device, because you can in many cases made some approximations around F mats and design like or made some expectations on transistor performance, which we will do shortly. I guess what you basically can show is that the gain looks something like this. It is 2u minus 1 plus 2 times square root of u minus 1, right? So, I mean, if I've gotten that right. Yeah. So, when u is equal to 1, right, this g again goes to, this is 2 minus 1, 1 plus 0, right? So, this is back to 1. So, at the frequency where u is equal to 1, once you put that invariant network, right, the gain again drops down to 1. Oh, so u here is the unilateral Mason's gain, right? And this is the gain that you can get if you put all the what do you call it, the feedback network around it, the embedding network around it. Okay? No, this is the best gain, maths gain with embedding network. So you can, there is a paper, this gain, by the way, this over here, this is called Singha-Kovinta's gain. Okay, so this gain metric, right, if you put that embedding network around, you can maximize the gain to this, right? But you can see that if there is some point when u is 1, you can see that g also becomes 1, right? So the point at which u is equal to 1 and g is equal to 1 are, let's call this gs, right? So gs is also 1. So basically what you end up with is that even that curve crosses the 0 dB axis at the same point. So when u is very, very large, so this number for u much, much greater than 1, g is 4u, right, approximately, right? So what basically happens is that you will, if I go back to that curve, right, you'll get some number that is 6 dB higher, right? And then it basically comes down and it will cross at the same point. Does this make sense? So, yeah, with those de-embedding networks, you can increase that, with the embedding networks, you can increase the gain. What the reference that I had with Nick Najad, and there are these papers by Momeni and Afshari. where they build such de-embedding networks in order to design amplifiers beyond 100 gigahertz, try to increase gain in the amplifiers, right? And there are one of the references that I put down, it also derives this, right? But effectively what you end up with is that Fmath still remains a good metric for transistor performance, raw transistor performance, right? No matter what you do, you'll be crossing 0 dB at Fmax. Is that it? And clearly, since all these curves, slope down with frequency, if I shift Fmax to the right, then that means that at my frequency of operation, I'm increasing the gain, right? Because all of these curves shift to the right. So shifting Fmax to the right always helps the gain at my frequency. We basically have these metrics of gain to design with, right? So let's look at our transistor model itself, right? So when we have our transistor, we basically have a native transistor model, right? Which we can basically say is CGS, CGD, and then we have a GM-VGS and GDS or RDS, right? So I'm ignoring the bulk, right? But you can add a GMB VBS if you want, right? We don't have to worry about it so much, right? So we have the native model of our transistor, right? And then on top of that, now we can basically start adding RS, RD, RG, and then maybe some wiring inductances might come in where you have LG, LS, right? And then you have some LD, and you might have capacitances, right, which are CdB, and you have a capacitance maybe over here which is CSB, right? And this capacitances end in the bulk, and then maybe you have like some resistance here, right? And then you have the bulk node, right? So what we have usually then is a model where we add these extrinsic parameters to our intrinsic parameters, because at the frequencies that we are operating in, these RG, RD, RS, they start impacting our performance, right? So we can now, with these parasitates, right, we can try to just evaluate how these parasitates impact our system, right? So let's look at FT, right? So traditionally, when we do FT with just CGS and CGD, and we have GM-VGS, right? So traditionally what we do is we basically put a short here, right? And we are trying to find out what this is IO, right? And this is IN. So traditionally we basically say that IO divided by IN, right, is effectively GM divided by omega CGS plus CGD, right? So this basically tells us that FT is omega T over 2 pi, right, which is GM divided by 2 pi CGS plus CGD, right? This is the analog usual derivation that we have. But now our circuit is a little more complicated, right? So let me just draw that out here. So I have again, let's say some IN, and now I have RG, right? And I have CGS, and then I have CGD. Then I have GM-VGS. I'm going to have an RS, right? I'm going to have an RD, right? And this is basically, technically I also have an RDS, right? Right? And then I'm trying to measure I out, right? So under the same scenario, what I can do is I can basically short my output, right? Where I'm trying to find out what this I out is, right? So when I short this output, I can basically, okay, I'm not 100% sure how to do that, so I'll just rewrite it. So I'll make some approximations along the way, right? I'll say that this CGS goes to ground. I know that this terminal and this terminal of CGD are connected through RDRS, but that's still somewhat small. So I'm going to call this the approximate network, right? So I can basically move this CGD out here, right? And then I'm going to basically have GM-VGS, right? RDS, and then some RS plus RD, right? And then this is the network that I'm sort of interested in. Actually, I mean, I shouldn't just make this CGD as it is. So let's just keep it as this, as it is here, right? And then we'll make the approximation. So this is CGD, right? So what I can basically say here is that this effectively looks like the Miller approximation here, right? Because there is going to be some gain. I can neglect this RDS in parallel with RS plus RD, but I effectively can show that this CGS, right? And then if I were to move this CGD to this side, right? I should do CGD times 1 plus GM RD plus RS, right? This is increased. And then I have GM-VGS, right? And then I have RS plus RD. And I'm interested in the I out that goes here, right? So effectively then I find that compared to the situation that I had, right? Compared to the situation that I had, if I do I out divided by IN, right? Now instead of GM divided by CGS plus CGD, I have GM divided by CGS plus CGD times 1 plus GM RS plus RD, right? So my omega t, right, my ft basically becomes 1 over 2 pi gm divided by CGS plus CGD times 1 plus GM times RS plus RD, right? So you can clearly see that the FT of my system is getting degraded because I'm adding this particular term to my denominator, right? So once you start including the parasitates, you can basically see that the high frequency performance of your system is beginning to degrade. So this is FT, right? So now let's look at Fmax of the transistor, right? So we'll do it the same way initially without this. So we have RG, right? And we have CGS, and we have CGD and GM-VGS, we have RO, right? And then we basically are looking for a frequency where we have maximum power transfer, right? So this is basically our input power source, right? Let's say we have some port which has some input impedance ZS, it can be optimized, right, BS. And what, so at really high frequency, what we can assume, so we know that at really high frequency, right, Fmax is high. So if Fmax is high, right, around Fmax, 1 over omega CGS goes to 0, right? So I basically can then just make a statement that my input impedance looking in, right, my Z in is just going to be approximately RG, right? And if my Z in is approximately RG, that basically says that my Z opt of my source or the Z max for my source should also be RG, right? That should also be RG by conjugate matching. Okay. So then we have Z out, right? So in order to measure Z out, I can basically put a test source here, VT, right? And then I can try to see, okay, what is the test impedance that I see, right? I'm going to see a current that goes over here, I'm going to see a current that goes over here, and I'm going to see a current that goes over here, right? And remember, when we can basically make an assumption that these two currents are dominant compared to this one, right? So we can ignore current through CGD. And we can basically make the argument that VGS is going to be VT times this capacitive divider. So that is going to be CGD divided by CGD plus CGS, right? So then you can basically show that the impedance that you see inside, right, or which is the output impedance that we see, is going to be 1 over RDS or RO. Okay, actually I've used RO there, so let's do that. 1 over RO, and then you have basically this current, which is GM times VGS. So that is GM times CGD divided by CGD plus CGS, right? So effectively, if I start thinking about this, this is basically my RO parallel, right? GM CGD. It's a reciprocal of that, right? So this is going to be CGD plus CGS divided by GM CGD, right? So this is my output impedance. So again, remember that by conjugate matching, I can basically say that my load is going to be conjugate matched to this one, right? So now if I think about my input power, so let's say I have some Vs and I have some Rs, and I know that it is basically driving a power into Rg, right? And this Rs is Rg. So if I think about my input current, right? My input current is going to be Vs divided by 2Rg, right? That's what my input current is going to be. So that input current flows in here, right? And I am interested in the how much power I transfer, right? and I am basically on the output side of it, I will effectively have an output current source driving my load, right? But I can effectively then say that at the input my Pin is going to be half In squared times Rg, right? That's what this is, right? And at the output, my P out is going to be half I out squared times my R out, right? And I know my R out from this. And if I try to do P out divided by P in, I get basically, so the current that is flowing I out, right, is basically I have a current source on the output side, right, and that is there is a source impedance, right, and there is sorry, not source impedance, this is the Z out of the device, and there is the ZL of the device, right? So as a result, I basically have some current going in here and some current going in here. But when I do conjugate matching and the real part of these are the same, I basically am going to have I out divided by 2 going in here, right? So, it depends on what, yeah, okay. So this is I out, then this will be I out by 2, right? So I should basically divide this I out squared by 4, right? So then I get my P out by P in as I out squared divided by 4 I in squared divided by R out divided by Rg, right? So now remember that if we go back to the Ft derivation, right? So at what we basically see is that I out divided by In as Gm over omega, I guess in the situation that we are analyzing now without Rgs plus Rd, it's Gm over omega Cgs plus Cgd. So what we can basically say that I out divided by In at any particular omega is basically omega t divided by omega, right? Because Gm over Cgs plus Cgd is omega t. So I out divided by I in at any particular omega is omega t over omega. So what you get over here is 1 over 4 omega t or Ft divided by F the whole squared R out divided by Rg, right? So the first observation here to make is that you see that the gain that you get, right? The gain that you get drops with frequency as the square of the frequency, right? So that's the first observation. And then if you want to equate this to 1, right? This for F maths, right? What you basically get is that F maths is 1 over 2 Ft square root of R out divided by Rg, right? But we already showed that this basically is going to be 1 over 2 Ft, and so this is 1 over Ro plus RDS plus Gm CGD divided by CGD plus CGS, right? And this whole thing divided by Rg, right? So you get this expression which you can further simplify to F maths is 1 over 2 Ft divided by square root of 2 pi Ft CGD RG plus RG divided by RDS. Right? So what you see in this is that both both CGD and RG are going to degrade your F maths, right? That's the first observation. And the next observation is there is a 1 over F squared dependence on the maximum gain that you get, right? So what this means is that if I know what my F maths is, and then I go F maths over 3, for example, that means that the maximum gain I can get is about 10 dB, right? So you can estimate how much gain you can get from your technology based on this, but you should optimize RG, you should optimize CGD in order to further reduce, in order to further increase the F maths that you get in the system. Now, I won't derive the whole thing with RD and RDS, right? But you can basically show that F maths with RD and RS included, right? You end up with something which basically looks something like Ft prime divided by 1 over 2 pi Ft CGD RG plus RG divided by RDS, where this Ft prime is the Ft with RS and RD included, right? So your F maths gets degraded further because of RD and RS, right? So overall, from a technology perspective, you're quite sensitive to RG, RS and RD, and you should try to optimize that in order to get better F maths in your device. And when you get better F maths in your device, at your frequency, you are getting better G maths because there is a 1 over F squared dependence in the performance. Does this picture overall make sense? Okay. This, by the way, I mean, we did everything for bipolar. If you do, we did everything for MOSFET. If you do bipolar, this term basically goes away because it doesn't exist for bipolar, right? Because the RDS or the RO is very, very high. So then you basically, instead of CGD, you have C mu, which is the base to collector capacitance. And this RG goes to the base resistance that you have in your system. Okay. So then from a device perspective, we would like to optimize the layout as much as possible, right? So the first observation that we have is that RG is a function of the number of fingers that we use in the device, right? And the number of and the finger width. So we generally, so for example, shown here is, I mean, this is an older paper, but I included this to sort of show the typical layout style. But basically, you try to minimize the gate resistance by doing double-sided gate contacts, not just one side, right? So you have double-sided gate contacts. A good design principle is to keep the width per finger to be 1 micron, right, of that order, right, 1 to 2 microns. And you try to strap the metals for the gates if you need a really big device, instead of trying to make a device with larger width per finger, what you try to do is build layouts like this, where you have split the number of fingers into a larger quantity so that the width per finger is small. And then instead of having a single long device, you have this sort of ring type structure basically, where the gates are coming in like this and feeding all these devices, right? And so if I think about this as the number of uh, ring stripe structures, let's say that's N, and then there is a NF, right? And then there is the width per finger that I have, right? So then this becomes my overall width that I have in my device, right? So these kind of layouts have been shown to have good performance by reducing the gate resistance. In order to reduce the source and drain resistance, again, you have vias pretty close to your transistors, and then you go up to higher metal layers as soon as possible in order to minimize the RS and RG. So here, each of these fingers, right, is basically the width that you have per finger, right? Yeah, this is a finger.
And these 4 are the number of fingers.
So here M would be 4, NF would be 1, 2, 3, 4, 5, 6. The width per finger would be what you would have here, right? And that would give you the total that you have. So the other thing that is done is some kind of staircase layout, which effectively, if I think about it from a 2D picture, so this is my transistor, so I would have M1 and then maybe my M2, and I keep building my vias, but as I keep going further and further, right, I am basically trying to increase the separation as I keep going in the metal stats, right? So that I'm minimizing, so if this is gate and this is drain, because usually, let's say you build a common source device, your source is ground, so it connects to your ground plane on a lower metal layer, but your gate is usually coming in from a high metal down to your device, and your drain is coming down from a low metal back to a high metal because it's connecting to some passive as well. But as we saw for the FMATs, you want to minimize CGD, right? So you want to reduce the overlap that you can have. So you want to basically keep separating this distance further as you stack up the device. So this is another thing that is done in order to minimize the CGD to improve the FMATs. These are good papers. I've put a couple of citations in here. And to the first order, once you get these principles, after that, you have to try a few layouts to see which one works, right? But these are the techniques that people use. The only other technique that sometimes your foundry will allow to do, or many times your foundry in their RF device will already do it, is that they will increase the pitch of the gates, right, on these fingers. They will so this is called double gate contact, and they might do double pitch, where they separate out the fingers by 2x as opposed to the minimum spacing that they can have for digital devices. And there have been papers that have shown that using double pitch can improve your FMATs FT to some extent as well. But there you run into a little bit of a challenge, because if that is not a model that is provided by your foundry, then you aren't sure if what you are simulating is what you are going to measure. But if you keep the underlying devices in terms of number of fingers and gate per finger, that is modeled. So then you can use that with the passives that you have and extract. Yeah, you always do RC extraction here to model the device for sure. The other thing that you can do is this concept of distributed modeling. Once your device starts getting really big, right? Then what you do is you basically make these unit cells, which might be one of those multi-finger arrays of devices, and then you feed your gate and drain like this, and then you're basically building a model for your device where you're basically adding inductors and capacitors as the along the device. So if you build a model like this, what for example, like in this interconnect, you're adding this L and C, right? So now you can basically create a situation where you're working with much larger device sizes, much larger number of devices in order to build a large transistor array. So where you make the separation is sort of dependent on the frequency that you are operating at, right? And how much these parasitates impact you. So this, for example, was done at 60 gigahertz. So all these parasitates mattered, right? If you're operating at a low frequency, then you might get away without it. Yeah, so it's effectively, you can think of this as multiple devices operating in parallel, right?
Very broadband.
Yeah, this gives you a broadband model. It works. So, for example, if you're designing, the one thing to remember is that your model cannot be accurate just at f0, because if you are designing and you want to check nonlinearities, what happens, then you are worried about what's happening at 2f0 and things like that. So you need to make sure that the model that you build is good up to the harmonics that you are interested in, right? So so the parasitic extraction has to be appropriate for that. In this particular case, the ground was there. There is a feed on, this particular circuit, there is a feed on the source as well. So therefore, it's a double driven device. It's driven at the gate and also driven at the source. And that's why the source is brought to the top layer. But typically what you would do is that you would have a ground plane like we discussed yesterday. And then you would effectively build your device inside it. So the source you immediately connect to this ground plane, right? And this ground plane is usually at your lower metal layer, and you're assuming that this ground plane is very low impedance because it's very big. So you make a big sheet of metal that way. So usually what you're trying to optimize is the gate and drain, because they're coming down from a high metal down to a low metal. And these VI inductances can be of the order of a few picohenry. So it's important to model those. Yeah. The biasing typically, it's taken separately, but usually depends upon how you do the biasing, but if you're doing the bias of an amplifier, for example, where you have a gate coming in like this, right? A gate bias, right? Then this resistance doesn't really matter for you. So you do all of this in the lower metal layers, right? You never bring up that bias contact. So that is going to go into the gate right at M1 or something like that, right? You'll just make the contact over here. And so biasing from a parasitic perspective usually doesn't impact you on the transistor performance, but if you're designing a PA, then you want a low impedance bias network. So then you are worried about the impedance looking in this way. So that becomes a modeling effort in itself, but not so much as an F-maths impact or an FT impact. That doesn't happen. In a practical layout perspective, so usually a good design start point is to take a unit cell device, right, that 10 to 20 microns wide, because those are the kind of numbers that you might end up with, and optimize it for layout. I was a little hesitant to use the letter M here because in Cadence, for example, there is a device multiplier there, and that basically is to use multiple such devices, right? That is what that means. But here this is basically how you are trying to split it into arrays, because if you don't, then you have a single long device, right? And if I don't do this type of ring type structure, I have a single device and then all my fingers are like this, and let's say my gate comes in like that, right? So by the time I get to these devices at the end, I have a lot of resistance that to get to these devices at the end. So I don't want to do that, and so I build something like this, which lets individual devices get fed by individual fingers. The gate resistance to them is minimized. It's a good question. I'd say it's frequency dependent, right? But the width per finger usually is somewhere in the 1 micron range, right? 1 micron to 2 micron range depending upon frequency. And then this distance is what, I mean, you typically can live with 10 to 20 microns device size on this side with an RC extraction, right? So then if your device is more than 1 micron times whatever it takes, how many ever fingers it can fit inside 10 microns, then you start going on this dimension and start building an array. So people will call this by different names. I mean, I've seen names like ring feed and things like that for it, but effectively you can see in papers that this layout makes a lot of difference, because if fmax moves by 10%, you're getting 10% more gain. So it just, not to my knowledge. The PDKs themselves, they optimize double gate contacts are available. There are some PDKs that let you set the pitch of the gates in the number of fingers that you have. So that is available. PDKs will sometimes enable M1 or M2 routing. They'll tell you, what layer you can bring it up to. So that is available. But this type of thing, no. This type of thing, you have to lay it out and do it yourself. That's basically what I was saying. You don't want this device to be very long, right? That's basically the problem. So if you, so in this approach, for example, I think this whole length is 27 microns, right? And in this particular one, he played around, for example, by splitting this and moving this 3 transistors into a 2D array, for example, right? So in the equivalent to that layout, we would have another 3 transistors over here, right? But in his case, the problem was that he had both gate and drain, all 3 gate drain source metallization. So he was having trouble once he extracted that with the GDS on top. For those 3 metals, he had to space it out, and that was increasing the parasitic cap. So he decided that it was better to do this way. And then he had to, the price for that is that you have to then model this, right? You can't not model this connection. Right. So that's basically the price. So the trade-off between number of, I think overall generally going for a square sort of arrangement is a good idea, right? That balances things as opposed to a long rectangle. You want to model the interconnect regardless, right? But what is the key metric that is most sensitive to all this is width per finger. That metric, if you make it very large, you immediately see an fmax impact. Because there the gate resistance is in poly, so it's not in metal. So it immediately adds to your RG and degrades your noise figure and degrades your fmax. The other approach that actually before we go to this thing, so one of the useful components that we typically see is that since fmax is basically constrained by CGD, right? So we see that it is right. So since it is constrained by CGD, right, there is a lot of interest in trying to find a way to basically remove CGD, improve fmax, and it also improves the stability of the device. So usually in differential pairs, very conventionally in millimeter wave, you will see this neutralization concept always, right? Where basically your, I'll actually go back to that. So you have your device, which is your diff pair, right? And then you're neutralizing by and So you're effectively playing this trick that the intrinsic device, which is like so, right? So this is this current, right? This current and this current are opposite in polarity, right? So you are basically removing, you are creating effectively a cancellation of the CGD, right? So this is something that is just a very popular approach when you're doing diff pairs, right? And what you can effectively show is that in this case the stability factor is basically, you see that it has a 1 over CGD minus, let's call this capacitor, so this is CGD and this capacitor is C neutralization, 1 over CGD minus Cn squared dependence, right? And so what that means is that if I basically look at the stability factor, so what you end up seeing is this kind of shape in the system, right? Where actually maybe I can just yeah. So if I were to just draw the stability factor, right? So this is, let's say, Cn over CGD, and I'm plotting the stability factor here, right? So remember, stability factor 1 is the desired thing. So then what you end up seeing is that you'll get basically a situation where, and this is 1 here, right? Cn is equal to CGD. So when Cn is equal to CGD, the stability factor sort of blows up, but below that it has this sort of shape, right? So both Cn a little larger than CGD or a little less than CGD end up in giving you k factors greater than 1, right? But when you run this, what you also see is that up to this point, there is no concept of Gmax, right? So all you have up to this point is maximum stable gain, right, over here. So Gmax is normally just GMSG, right, because you just, k is less than 1, so you don't have Gmax. And over here you have Gmax, but we already saw that in situations where k gets to be very, very high, Gmax will basically start dropping, right? So you end up seeing a shape which basically, from a maximum gain perspective, you end up seeing a shape that looks like this, right? So now you have a trade-off to make, right? Where we can either design at this point where we know the device is very, very stable, but then we give up gain, right? So typically you might end up designing somewhere over here, right, where you decide that there is a gain that you want to have, and so you don't neutralize the full CGD out, right, but you neutralize it partially out so that you get a balanced trade-off between stability and gain. And how you implement this, so people have implemented this with native devices that are matched to your NMOS, so that let's say that if this is a certain W of this device, right, I implement this capacitor using a MOSFET with a W1, right? And so by scaling W1 to W2W, I am basically scaling the Cn to CGD. So this is one way of doing it. The common way of doing it now also is to build it as part of the layout, right? So shown here is a layout like that, where basically what you're trying to do is you're trying to overlap the gate and the drain, right? And this is, it's a bit hard to make out, but this is basically G1 and this is D2. So you can clearly see that over here, right? and this is D1, G2. So there are these capacitances that exist between these devices, between these wiring, right? So just by using the metal wiring and this this sort of structure over here, right? What you can effectively do is include the neutralization pair inside your individual neutralization transistors inside your transistor layout, right? And by doing extracted simulations, you can figure out where you, so you typically see this sort of shape in your system, right? So you can effectively design to pick a particular design point that will work from a gain target perspective. This won't track process, right? You're relying on metal parasitates to do that. But again, you're not, you don't want to be here either, right? But what you basically, you try to pick some value that is over here, which is within, let's say, you're within 10%, you can live with that sort of trade-off. So that is a designer approach. If you do lay it out with devices, you do have this problem of going out to those devices. So those are extra parasitates that end up limiting the Fmats that you were fighting so hard to get in the first place. So this kind of approach now is quite popular to get neutralization. So we have a figure of merit for our device, right, in terms of Fmats, because we know that so Ft basically all it captures is the current gain of our device, right? But Fmats captures the power gain of our device, right? So we know that then power gain basically has a 1 over F squared dependence, right? So, or Fmats over F squared dependence, right? So we can effectively estimate how much gain we can get at our frequency once we have Fmats, right? So that is this thing. We've seen some layouts, right, that optimize Fmats, right? We also have seen some, if you think about it one way, the adding that CGD is a little bit like unilateralization, right? Because you're adding a feedback to basically remove the Y12 term, right? So we have seen basically that with diff pairs, and there are networks even with single-ended transistors through transformer feedback, right? You effectively can lay out, right, with neutralization to get good Fmats, right, to improve Fmats. Actually, I guess I shouldn't say Fmats, but just to improve Gmats, right, for the pair. Right? So now the question is, how do we bias the device, right? And here, fortunately, there's a somewhat reasonable way of doing this, which is that what we find is that instead of thinking in terms of bias voltage, if we think in terms of bias current density, right, we are able to evolve a very systematic approach, because what we see is that, so in this particular paper, what they tried to show was that if I take a device Fmats, and on the x-axis they are plotting IDS over W, which is the current density of the device, right? And what they are showing is that the optimum current density for Fmats has stayed relatively invariant across process technologies, right? So in CMOS, effectively, if you bias your transistor in the 0.15 milliamp to 0.3 milliamp per micron range, right? You basically are biasing your device at the optimum Fmax. So then effectively the transistor design process would basically be that you can, if you know what ID that you need, you know that there is an ID over W that optimizes Fmax, right? So you use that ID over W, that current density, to determine the W and bias voltage. Right? So you can run these simulations for your technology of choice, right? And these numbers, I mean, all of this is, of course, we are trying to maximize the gain by trying to maximize Fmax, right? But there are other metrics as well. If you are more worried about FT, right? Even FT has an optimum bias current density. And it turns out that if you are designing for noise, even noise has an optimum current density for noise. So you bias your device based on what is it that you're trying to optimize, Fmax, current, FT, or noise, right? But once you get that density, you can bias your device. So from an amplifier perspective, then you there is a little bit of an iterative process within that. You do a layout, right? And then you find what is the maximum current density for that particular layout, right? And you find out what that Fmax is, but you iterate it a couple of times until you find out a good Fmax and current density combination, and that becomes a unit cell that you use in your design.
The CMOS is even the SOI.
Yeah, so it differs. Yeah, I mean, that's why this, like, I mean, I think it is a little bit of an exaggeration to say that it's completely invariant, right? Because SOI, FinFET, all these things are coming along, but it is in that range. It is in that range, 0.15 to 0.3 milliamp per micron. And you can run a simple sweep, right? And you can determine for your particular technology right at which is the best bias that you can have. And it's true for bipolar transistors, sort of in that current density as well.
PA design specifically.
Yeah.
Is there thermal considerations to do optimizing?
For PA designs, usually at millimeter wave, you are starved for gain. So you are trying to bias close to Fmax anyway in order to get enough gain from the device. But once you are there, I wouldn't say that thermal considerations impact the width per finger, that current density that you use is yet. I wouldn't say that's true.
Even in SOI?
Even in SOI has some self-heating, but I mean, the output powers that you are getting at millimeter wave are still of the order of hundreds of milliwatts. It's not that you're not doing some watt level device. In watt per millimeter squared in CMOS is still only about, I think, 50 milliwatts per millimeter, something like that. So it's not a large number that you have to worry about current density through the finger. So each metallization in CMOS, I think, can. So I think the higher metals can take something like 10 milliamp per micron, something like that. So again, you might be limited in the sense that you want to make sure that your metals are thick enough and wide enough to handle the currents that are going through. But that's more how many fingers you pack, how tightly spaced, not a current density question still. Yeah, so that is, so at this point, then we know how to lay out a transistor, we know how to bias a transistor, right, in order to get optimal performance. Now we have to figure out the conjugate matching networks or passives that we have, right? So we design these passives in the back end of the line. So shown here is a sort of example back end of the line that is there in technologies, right? The key things that, we mentioned this yesterday, that we are usually interested in is the thickness of the top metal layers, the height of the metal layers above the lowest metal layer and the substrate, right? And the substrate resistance itself. and all of this usually impacts performance, right? This is a low resistivity substrate, right? 13.5 ohm centimeter. But nowadays, you get in SOI technology substrates that are pretty high, that are of the order of 1 kilo ohm centimeter. So it basically improves performance. Then I'm not going to, since there is a lot of familiarity with inductors, I will just give a very broad overview of it. But the passives that we need are inductors and capacitors, right? So we will first begin with inductors and then discuss them. So the way that we build inductors is that we just make effectively on-chip spirals, right, in the top metal layer, for example. This is a single turn spiral, right, that you would just make. This subject is not very different from what you do at RF, right? This is basically the design principles are effectively the same. And the only things to note as we move to higher frequencies are our typical model for this looks like an LS, a series inductor. This is what we call the pi model for this, right? That there is a capacitance, and then there is capacitance that then goes on to the substrate. Right? So this is typically the pi model for the inductor that we work with, right? And this RS is basically the series resistance, and it is coming from both the wiring resistances that are associated with the metal wire itself, and also from the substrate losses that happen because eddy currents get set up in the substrate. So when you have a current going like this, the substrate is trying to generate a current in the opposite direction to cancel the magnetic flux, right? So those losses end up showing here. The one useful thing to remember here is that we have this concept of skin depth, right? Which is that effectively what happens is that if I have a thick metal, the current basically only travels in the periphery of the metal, right? With a depth delta, right, which is square root of 2 over omega mu sigma, right? So what this means is that depending upon the conductivity of the material that you're using, this skin depth changes, right? But if you were to just get some numbers in here, the conductivity of copper is 5.8 to 10 to the power 7 Siemens per meter, right? So that basically tells you that copper is somewhere, if I'm not wrong, copper is around 0.3 microns at 50 gigahertz, and 0.6, around 0.66 microns at 10 gigahertz, right? So given this scenario, basically, then one thing that we should remember is that it still helps to have a thicker metal, right? Because if you have a thicker metal on this side, right, you are increasing the area of the conductor, right? And what this also means is that our series resistance, right, is rho L divided by area, right? And the area is to the first order, the area is sort of delta times the perimeter, right? So if this is W, this is the thickness of the thing. It is sort of proportional to the width of the material and the thickness of the material, right? So that's basically the area. So what we effectively see is that as we increase the frequency, this causes a square root f increase in the because the skin depth is reducing as frequency goes up. The sheet resistance effectively is going up as square root of the frequency, right? So this would mean that the quality factors are getting a little worse as you increase. But on the other hand, the inductances that you need at these frequencies is also smaller, right? So the length that you are using is less. So that basically means that the resistances are dropping, right? So overall, you can basically get, so the metric that we use for all this is quality factor, which is L omega divided by Rs, right? Is the Q of the inductor. So this is basically the amount of reactance that you are getting and the loss that you are paying for it, the resistance that you are paying for it, right? So this metric you can get from 15 to 20 at millimeter wave, right? So you can build inductors with these kind of quality factors, particularly on high resistivity substrates, right? So with these kind of inductances, with these kind of quality factors, you can build useful circuits. But you should also remember that this CS matters, right? Because effectively, for example, if I have a situation where I am operating this inductor as a inductor where my model is basically that this side of the inductor is connected to ground, let's say, right? So then if I look at that model, I'm basically having an LS, I'm having an RS connected to ground, and then I have a CS that is also connected to ground, right? And then I may have this capacitance over here, right? Which I'll call C sub times C odds divided by C sub plus C odds, right? Connected to ground. So now when you look in here, you're not just seeing an inductance, you're seeing an inductance in parallel with two capacitances. So we have this concept of self-resonance, right? Which basically implies that you think you have an inductance, right? So if you have an inductance, you would see, for example, that if I look into this and I try to see the Z that I would see, right? I would basically, if I didn't have anything, I would see a Z of j omega L, right? So if I plotted the imaginary part of Z, right? So then if I were to make this plot, right, I would see something like this, right? But now if I consider this, I'm basically seeing j omega L in parallel with some 1 over j omega C, right? Right? So at really high frequencies, this, if it is dominated by this, right, I'm effectively seeing a short. So I might see actually something that looks like so, right? So you end up with a situation where so you end up with a situation where you have self-resonance in your device, so you can't operate it as an inductor beyond a certain frequency, or more effectively, the inductance that you see is not Ls, right? You are seeing an effective inductance that is changing. So you have to account for that. Then just to very quickly summarize things to do for quality factor, right? What you want to do is you want to increase the width of the device, right? And sorry? Oh, okay. So that okay, maybe we can, yeah, we can come back to that, right? So let's actually, if you want, we can analyze it, right? So this is j omega L, and this is the free. This is like the C. Let me just call it as CS. Let's assume that that CS dominates and not the other one, right? Or let's call this C total, just to keep that in the picture, right? And I have RS as well, right? So let's say that I'm ignoring RS for now, right? So if I consider my Y in, right? My Y in is 1 over j omega L plus j omega C total, right? So if I write this, I can write this as Y in as 1 over j omega L times 1 minus omega squared L C total, right? And this then effectively means if I can define an inductance effective, right? So L effective at omega becomes L divided by 1 minus omega squared L C total, right? So what if you are aware that your inductance is changing, right? Then you can use it up to whatever frequency you want. But the problem is that you will not be getting the exact frequency that you think you are getting, right? That's basically the issue. And in particular, if you're trying to design something wideband where you're counting on the L to be the same, then you have something where the L itself is a function of omega and that is changing. So people will operate where so let's say that this is L divided by 1 minus omega by omega SR squared, right? Right? So if I am basically, let's say my omega SR is of the order of 2, right? So this ratio is 2, then this becomes L minus 1 over 4, which basically becomes 3L over 4, right? So I'm, sorry, 4L over 3, right? Sorry. It should be higher, right? Right? So I'm basically getting a slightly larger inductance than I thought I'd be getting. But you can also in design consider a scenario if you're using it like this, where your design itself maybe also has a C load that comes in parallel with it, right? So if you are willing to accommodate this C total into the C load, if you're willing to absorb it, right, then the whole design starts working out again. So up to what frequency you can use it is not a straightforward question. It depends upon how you can absorb the parasitic of this into your network, right? So that becomes the way in which we design. So you could easily see people observe operating inductors at 70% of their self-resonance frequency if you take the inductor standalone. But that's because the load is already accounted for the inductor capacitance. So then you're okay with design, right? In fact, this happens in transformers quite often. So it isn't a bad thing that this capacitance exists, right? And it is important to be aware of how you are using it, because let's say you decided to make your inductor very thin because you were trying to minimize this capacitance. You are actually doing a suboptimal design, right? Because what you could do is absorb it inside this and then use a wide metal layer for this inductance so that this resistance drops, right? Now, having said this, the only other caveat that I would say is that this model itself, as we discussed when you're talking about lumped in distributed circuits, is not a wideband model. So if I want to truly make a wideband model for this inductor, I maybe divide this inductor into 4 sections, and for each section I have this model, right? And once I have that model, I then try to see if I can absorb the parasitates inside this, right? So at millimeter wave, you are counting usually on absorbing parasitates, because if that doesn't happen, if each component is designed standalone, that's an inefficient way to design the system. Does that answer your question? So yeah, 70% of FSR, 60% people use all the time, just as long as you're able to absorb the load. In fact, many times this is a very significant fraction of your load itself, because you're designing around that. Okay. So coming back to the quality factor question, you're trying to, you can increase the width of the metallization to increase the quality factor, right? In general, increasing area helps, right? So you can make your inductor larger, right? And make the width of your inductor more. So that will reduce your inductance per unit length. But because you're using a larger area, it will increase your overall inductance, but that helps get Q, right? And the other note probably is that you have to account for metal fill in all this. So inductor Q is usually degraded by 10% at least if you start putting metal fill. So most foundries underneath this area, right, will let you fill with a lower density. So one should leverage that and reduce the density of the metal that is inside this, right? So that you are basically reducing the quality factor degradation. And again, how we choose to use the inductor matters. So the same inductor, when we were using single-ended, looked a certain way. But if we are using a differential, for example, then what you would find is that these capacitances and resistances would show up in shunt, right? So you have to think about the inductor model that you are using, whether you're using it differentially or single-ended, to figure out which of those resistances matter for you, right? For example, if this port is grounded, then all of this side doesn't matter, right? So it's something to keep in mind. This basically shows some typical inductors and transformers that you see, right? And you see this self-resonance sort of impact happening where your inductance is going up across frequency, right? Effective inductance that you see. So one thing that people do is that, let's say that this is my top metal layer, right? MT, and then let's call that Mn, and this is Mn minus 1, right? Then you might build an inductor by just strapping these two metal layers together, right? So that you're basically increasing the effective width of your inductor. This is a technique that works well to improve Q as well, right? Yeah, and you can see that the sort of areas that you need, right? You need about 50 microns, for example, to get 100 to 200 picohenry order of inductances. And the quality factor, like I said, it's I mean, in this technology, it's 10 to 15. If you put a high resistivity substrate, it actually goes from 15 to 20. You can get those kind of quality factors. The other thing at millimeter wave, a useful thing to do is this, which is that you build your inductors with ground planes around them, right? And while this decreases your inductance a little bit, because again, there is a current going this way, and this is setting up a current in the opposite direction, right? Because you have a ground plane there. So it reduces your inductance a little bit, but it is still very useful for isolation purposes. So for example, shown here, they ran some simulations where they basically show the inductor coupling without a ring and with the ring, right? And they basically demonstrate that you can effectively get quite an improvement in the coupling when you start putting ground planes around them. So the usual thing that happens at millimeter wave is that the inductances are short, right, or small. So you don't have a lot of room, even if, for example, you want to physically space two inductors, the wiring to get to that longer space might itself be a significant fraction of the inductance that you want. So for example, let's say that I have some gate inductance and I have some drain inductance, right? And I decide that I want this to be separate. So I do a gate here and I drain here and I put my device over here. Then in order to get to this point and to go to this point, this L wire G and L wire D might itself be a significant fraction of this, right? So it isn't that I can always place these very far apart. So I have to think about how to distribute the inductance that I want between the wiring inductance and my inductor itself, right? And then I also have to make sure that I isolate. So this is a very commonly used and good practice to do, where you surround your inductor with a ground plane in order to get better resolution. So I mean, these days showed that the Q doesn't hurt very much, right? But you can see, for example, in their case, they are seeing that this is their L, right? And this is the L inductor with ring and L inductor without ring. And in that case, they are seeing a higher self-resonance frequency, because effectively, I guess the claim would be that the capacitances here are impacting them, right? But it depends a lot on how you space this, how far you space this inductor from that coil, right? But you can have a, so if you have a, I guess the way to think about it is that when you, if you, an inductor, or you can think about it as a transmission line, but you have a wire and then you have a ground, right? So whenever you have impedance, it is square root of L over C, right? So by decreasing this, increasing this capacitor, you are effectively reducing the Z of your system, right? Which is effectively like saying that you have a smaller L in your system. So it can, if you put the ground plane very close to it, reduce your inductance that you see in the design. The general approach, yeah, I mean, is that you just have to put that exact structure that you have in the simulator. There isn't any magic there, right? That you just basically have. I'll draw the signal and the ground over here, right? This is the pad, and if your pads are far apart for packaging reasons, right, what you end up doing actually is that you bring your ground plane quite close to your pad, right? So that's the first step that you do, that where you are making contact with the pad to this point is a very small resistance, and then over here, let's say that you have this and you have this, you have your signal trace coming out, right? And then let's say that you have an inductor. I'll just draw a 1.5 turn inductor going out, right? And what you do is around it, you are basically modeling the ground. You are placing a ground, right? So now the discontinuity that is happening is this particular part here, right? Because the signal and ground are quite close, but eventually when you are making contact on your board, on your wire bond, on your bumps, flip chip, whatever you do, there is discontinuity here, right? And the only way to do it is actually to model discontinuity. So you basically, let's say that you're doing a flip chip. So there is usually a pillar here and a pillar here and a pillar here, right? So you put this exact network into your simulator, right? And you get the S21 of this part, right? And then you design your inductor with that S2. So that's basically the whole network. Anecdotally, I will say that this doesn't, so at frequencies like 30 gigahertz, this doesn't hurt you that much. But as you go higher and higher, it does. There have been papers which have tried to make what they call a transparent line by trying to adjust this shape over here to make it seem like a smooth transition and make it 50 ohms. Works to some extent, but end result is that this is what you have to do. You have to take your ground plane, put that, model the bumps, and then on your PCB you have a ground plane. You have to model that whole thing and model the transition. And usually it ends up, usually it depends upon the bump size, but it can end up like it looks like a capacitance discontinuity. So you have basically a 50 ohm line and then a capacitance and then maybe something that loads 50 ohm. So now you have to design your network to accommodate this. So coming back to the inductor itself, I think overall you can also see, I mean, there's one simulation that is worth looking at from this paper, right, where they looked at the impact of substrate resistance on the Q, right? And what they showed was that, that you can get to these high Qs as you increase the substrate resistivity, right? You don't have to go up a whole lot, but if you even go up to 100, right, from the 10 ohm centimeter substrates, you go to 100 ohm centimeter substrates, you can basically get Qs, but beyond that it starts saturating out, right? So this basically is the sort of design that we just discussed, right? You see here that they have the inductor, they have the ground plane around it, and what is feeding the inductor and what is coming out of the inductor, that's like a transmission line. If you have the transistor single-ended, right, you are designing this matching network.
So no differential.
That is clear that nothing, it does nothing, right? It doesn't matter what component you use inside this network. That doesn't matter. Now, if you are using a differential pair, right, I can treat the diff pair also as a 2-port input. It's just plus minus ports instead of ground and reference ports. That's a 2-port as well, right? And if you are going to make that 2-port, that inherent, let's say that I do a differential 1-port here and differential 1-port here, right? And I measure the differential S parameters, right? And that basically is my, I'll call it SD, right? And that, if it shows some instability and all that, again, building a differential matching network is not going to change anything for that.
So common mode effects.
If you are, so then if you excite this in common mode, right, and let's say you have some common mode S parameters, I'll call that SC, right. Once you have that common mode S parameters, your use of the coupling, or it isn't that which is improving stability. What is improving stability is that you are implicitly introducing some loss. As an example, what you might do is that, let's say I have a network, right, where I have an amplifier, just as an example, right, and I have these 2 inductors, right. So differentially that's AC ground, right. But in common mode, let's say that I introduce a resistor over here, right. Or even more commonly, let's actually do this because this is something that actually people do, right? Let's say this is a cascode pair. Right? In AC, this is a ground. I can put a resistance over here, right, and bring my V bias for this way. So, my network in common mode changes because I am able to introduce a resistance that does not exist in the differential mode, and that resistance stabilizes my design. So, it is not so. Similarly, I might choose, for example, to introduce this resistance here, or I have this scenario where at my input I have a differential inductor, and this common mode point, right, I start putting a resistor to bias this, right. I can make my network for common mode and differential different to introduce stability, but that implicitly I think says that in common mode you are trying to introduce some loss in your system. Just to discuss the second set of passives that we use, these are capacitors. So, with capacitors, there are two kinds of capacitors that people use in millimeter wave, MIM and what we have many names for this, metal oxide metal or vertical natural capacitors. So, there are, I'll sort of highlight what those are. But MIM, effectively the idea is that you usually have a separate metal layer with an extremely thick thin insulator, right. And then you are basically making contact to it again in your metallization, right. So, this is a metal insulator, metal capacitor. So, that usually implies having a very a separate device which is a very thin insulator, usually silicon nitride in there, right. And for this capacitor, again we have to come up with some model that includes a series wire-in resistance, right. You have this resistance, you have this resistance, you have some inductance here, some inductance here, and then there is some parasitic capacitance here, right. So, this is the actual device that we are trying to use, right, but in using that device we are introducing all these parasitics. So, you have to model this device with L, R, C, and then we have the C outside, and this basically again I should call this 1 and 2 because these are not symmetric, right. So, effectively what you have is a parasitic capacitance at the bottom plate of the transistor of the capacitor, right, and inductances and resistances in series. Same situation happens that this is HC, right, which is 1 over j omega C series which you targeted, and this is the inductance which is j omega L parasitic, right. So, and you have some wiring resistance, right. So, you end up with the same sort of issues. You have a Q of the capacitor that is 1 over omega Rs Cs, right. So, this basically is the Q of the capacitor that you can have. Again, you can get order of 15 to 30. So, it depends upon the capacitances and stuff like that, right. But with just to give you some order of magnitude numbers here, right. So, if you have a 200 femto capacitor, you can get Q of 15 to 30 at 30 gigahertz in that ballpark, right. So, usually this has a capacitance density that is 1 to 2 femtofarad per micron square, right. So, you can then see that clearly if I think about this again, I have Z as j omega LP plus 1 over j omega Cs, or I can write it as 1 over j omega Cs times 1 minus omega squared LP Cs, right? So this basically again creates this situation that my C effective is Cs divided by 1 minus omega squared LP Cs, right? So I have the situation that the capacitance that I see effectively increases because of this wiring parasitic, and you can effectively show that if you keep increasing the size of your device, if you use a larger and larger capacitor, what you're going to find is that your self-resonance frequency is going to drop, right? So practically a few hundred femtofarad is fine at millimeter wave, but again, something to keep in mind when you're simulating. And then we have these things that we call native capacitors, right? And native capacitors are ones that don't require this extra thin insulator. So basically they are being made with only the metal back end of the line that we have, right? So in this there are, so basically the way to think about this is that you have, so this paper talks about how these MOM capacitors have moved across nodes. So I've taken some figures from this paper, but effectively what you see is that you have one metal, right? So this is one metal and one side of it, and this is in the same metal you might choose to put another set of fingers like this, metal fingers, right? I'm obviously drawing the spacing between them more than they are, but you'd like to make those spacings as small as possible, right? So you are now counting on basically the capacitances that exist between these metals, right? So you're able to create capacitances like this, right? So you can actually now you can imagine that you can do it. If I take a side view of the system, right, I can basically have sorry, let me just go back to the color. So I can have one layer like so. So and this is the other finger, right? And then in the next layer again, so this is Mk, this is Mk minus 1. I can basically do this again, right? So you get the picture that by using many metal layers, right, I can create parallel capacitances effectively. You have to imagine that all of these are wired together, right, in some way across metal layers, and similarly the other metals are wired together. So you have all of these capacitances that exist, right? So now you're using multiple metal layers to create these capacitances, right? So all of these capacitances exist. Now as soon as you do this, you realize that, hey, I can get even better if I distribute the two layers this way, which is that I make the first layer like this and like this, and then the next metal layer I do this, right? So now I am creating a situation where I have capacitances like so, like so, like so, right? So I'm basically increasing my capacitance density. So you can do that, and then you can do the equivalent also of the via wall, where across metal layers you can have one side which is, so these are vias, right? And then the other finger basically looks like so. Right? And so there are multiple ways. So usually from a designer perspective, there is choice in the number of metal layers you're choosing and uh, uh, the number of metal layers you're choosing, and sometimes maybe even in the arrangement of the metal layers. But effectively what you're trying to optimize usually is the capacitance density. And yeah, if we look over here, you can see the metrics that people have. So across technology now, as the metal layers get denser, you can get 1 femtofarad per micron squared in each layer, right? This is in each layer. So if I use 4 layers, I can get up to 4 femtofarad per micron squared, and this sort of shows what's happening, right? So as you look at the latest process with 8 or 9 metal layers, I can actually get 8 to 9 femtofarad per micron squared. So you can get really dense capacitors, but from a millimeter wave perspective, you don't always want to use the lowest capacitors. You want to, because the lowest metal layer sheet resistance is poor, so you might give up some of the density for getting better Q, right? And these Qs are again of the order of the same sort of numbers, which is that if you are using them like similar to MEMS, you can sort of get 20 type numbers. The one interesting thing here is this paper, which basically talks about how to feed these MEMS. So what it basically says is that if you're feeding these MEMS at the edges, right, feeding these MOMs at the edges, then basically across all fingers, let's say this is a plus port and this is a minus port, across all fingers the current flows in the same direction, right? But if I choose to feed this in the middle, then I basically have this situation where the currents in the positive and negative fingers, or the finger 1 and finger 2, they are going in the opposite direction. So we get this phenomena of self-inductance cancellation. So so this is in general a good practice to do, to feed the so these are the two plates of the ports of the capacitor, right? But instead of feeding them here and here, they're sort of fed in the middle here and here, right? And this approach they show basically gives you a little improvement in Q and also the self-inductance cancellation. So what you can see here is that this capacitance, when fed from the side, as I increase frequency, the capacitance increases because of that LS effect. But when I feed in the middle, this basically stays pretty flat across frequency. So this is a useful approach. The other thing that is usually of interest here is that I create some CS, and then I create the C parasitate, which is to the bottom, right? Because of the way that all the capacitors are there across all metal layers, and then there is a parasitic capacitance to the substrate, right, that exists. So I want to reduce this C parasitate, then I should avoid using the lower metal layers. I should move up, right? But if I use fewer metal layers, I'm reducing my density, so I'm increasing my area. So then if I increase my area, again I'm increasing C parasitate. So there is a trade-off. So they talk about having this CS by C parasitate ratio, right? And what they suggest, or what people usually do, is to leave out the bottom 2 or 3 metals and use the higher metals, because if we do that, then we sort of get the best possible ratio that we can get here. So for the capacitance that we are adding, the parasitates that we are using are less. So from a Design perspective overall, many technologies now feature only this native capacitors, and with this native capacitors, feeding them in the middle and making sure that you're not using the lowest metal layers, you can get up to capacitance densities which are of the same order as the MIM, if not more, right? And you can get Qs that are, I mean, these Qs are a little on the high side, I would say, but if you start putting some more wiring in them, so these, you know, suggest Qs that are of the order of 25 at 30 gigahertz, right? So as you put a little bit more connection than perhaps is included in the paper, you will start seeing somewhat lower Qs. But Qs of 20 for 200 femto order capacitances are quite reasonable to expect at 30-40 gigahertz with these technologies. So this doesn't work very well if you use only the top metal layers, because the thick metal layers have a lot of spacing requirements between them, so your trap density drops. It doesn't work very well if you use the thinnest metal layers, because they are too thin and their series resistance is too high. So using intermediate metal layers works nicely. If you have limited number of metal layers, then that is a problem, right? So with those mid sort of layers, 1 femtofarad per micron is achievable. Initially, when people built these kind of capacitors, they were trying to build really, really dense capacitors for bypass and things like that. So at millimeter wave, we still use them for bypassing. We even use the lower metal layers in order to bypass. That's fine. But if I'm operating a technology with 4 or 5 metal layers and the only top metal layers are thick, right? Then maybe this is not the great approach. So then I hope that I have a MIM. If I don't have a MIM, then I try to use transmission lines as shunt stubs, open stubs, in order to emulate capacitances. So that's basically what is done in the MIMIC world, where they don't have capacitors, right? There, when you want a capacitor, you have a transmission line that is open, and you try to emulate a capacitor that way. So that's what we end up doing. But most technologies now have pretty well characterized native capacitors. So the other thing is that modeling accuracy matters here. If I run just an extraction, it doesn't work very well. Just an RC extraction doesn't model this. So I either have to run EM sims, or I have to rely on the foundry models to be accurate. So most foundries now that are millimeter wave centric offer this as an option, particularly the CMOS ones.